Imagine a computer so powerful it can solve problems our current computers would take thousands of years to solve. Sounds like science fiction, right? But it's not. Welcome to the world of quantum computing. This isn't your everyday computer. This is a realm where bits transform into qubits and possibilities become endless. From solving complex mathematical problems to modeling atomic structures, quantum computing is a paradigm shift, a leap into the future. Intrigued? Then it's time to delve into the fascinating timeline of quantum computing. The concept of quantum computing did not emerge overnight. It's a product of years of scientific exploration and discovery. Quantum computing has its roots in quantum mechanics, a branch of physics that describes the bizarre behaviors of the smallest particles in the universe. The theory of quantum mechanics was born in the early 20th century, with scientists like Max Planck and Albert Einstein leading the way. However, it wasn't until the 1980s that the idea of quantum computing began to take shape. Scientists like Richard Feynman and David Deutsch began to wonder, if quantum mechanics can explain such strange phenomena, couldn't we use it to perform calculations far beyond the reach of classical computers? Thus, the theoretical framework for quantum computing was born. This was a time of extraordinary intellectual ferment, where the unthinkable became thinkable, and the impossible seemed within reach. By the 1980s, the theoretical groundwork for quantum computing was set, but turning theory into reality, that's a whole different story. The journey from theory to reality is often fraught with challenges, and quantum computing was no exception. As we delve into the history of quantum computing, we find a path riddled with obstacles. Yet it's a path that has led us to one of the most promising technological revolutions of our time. The first quantum computers were mere prototypes, simple and crude, yet they held the potential for something extraordinary. They were a far cry from what we have today, but they represented a crucial first step in the journey towards a quantum future. The development of these early models was marked by significant breakthroughs. One of the most notable was the realization of quantum superposition and entanglement, two fundamental principles of quantum mechanics in a computing system. This was a monumental achievement, a testament to the tenacity and ingenuity of the scientists involved. Yet they weren't without their fair share of setbacks. The delicate nature of quantum states posed a serious challenge. These states are extremely sensitive to their environment, and any form of interference could cause them to lose their quantum properties, a phenomenon known as decoherence. This was a significant hurdle to overcome, but it wasn't insurmountable. Engineers and scientists worked tirelessly, developing new techniques and technologies to maintain quantum states for longer periods. Innovations such as quantum error correction and fault-tolerant quantum computing were born out of these efforts, and they have played a crucial role in the evolution of quantum computers. From those rudimentary prototypes, quantum computers have evolved into more advanced systems. Today, we have machines capable of performing calculations at speeds that were once thought impossible. They are more stable, more reliable, and more powerful than their predecessors. It's truly remarkable how far we've come. Yet, we must remember that this is just the beginning. Quantum computing is still in its infancy, and there's so much more to explore, so much more to discover. The journey from theory to reality has been a long one, but it's far from over. These advancements brought us to the quantum computers we see today, but what does the future hold? Quantum computing is still in its infancy, but the potential is enormous. So what can we expect from the future? As we delve deeper into this new era of computing, we can expect quantum computers to become more powerful, more accessible, and more integrated into our daily lives. Imagine a world where complex mathematical problems that would take a conventional computer millions of years to solve could be cracked in mere seconds. That's the kind of computational power we're talking about with quantum computing. As quantum computers become more advanced, we could see breakthroughs in areas such as cryptography, where quantum algorithms could shatter the security of current encryption methods. And it's not just cryptography. Quantum computing could revolutionize many industries. In pharmaceuticals, for example, quantum computers could simulate molecular interactions at an unprecedented scale, potentially leading to the discovery of new drugs and treatments. In finance, they could optimize complex trading strategies and manage risk more efficiently. In logistics, quantum algorithms could find the most efficient routes for delivery and transportation, saving time and reducing emissions. But the future of quantum computing is not without its challenges. quantum computers are incredibly delicate and require a level of precision and control that is currently beyond our reach. They also need to be cooled to near absolute zero to function, which is not exactly practical for everyday use. Plus, there's the question of quantum error correction, an essential feature for reliable computing that's still a work in progress. Despite these hurdles, the potential rewards are too great to ignore. Scientists, engineers, and tech companies around the world are racing to overcome these challenges and unlock the full potential of quantum computing. As they do, we can expect to see quantum computers becoming more commonplace, perhaps even finding their way into our homes and offices. The future of quantum computing is a thrilling unknown, promising to revolutionize our world in ways we can't even imagine yet. But one thing is certain, the quantum revolution is coming, and it's going to change everything. So we've journeyed from the birth of quantum computing to its exciting future. But what are the key takeaways from this exploration? We began with the inception of quantum computing, a concept that emerged from the realm of quantum mechanics, the theory that governs the smallest particles in the universe. This concept was a radical departure from classical computing, introducing us to qubits, superposition, and entanglement, the fundamental principles that allow quantum computers to perform complex calculations at speeds unimaginable to classical computers. We then moved on to the realization of quantum computing. We explored how the first rudimentary quantum computers were built and how they've evolved into today's quantum systems, capable of solving problems that were previously thought impossible. We learned about breakthroughs from research institutions and tech giants, propelling us towards a new era of computing. Looking ahead, we delved into the future of quantum computing. We discussed its potential to revolutionize sectors from cryptography to drug discovery, promising solutions to some of the world's most challenging problems. We also touched on the hurdles that lie ahead, including the need for robust error correction and the challenge of maintaining quantum coherence. Quantum computing is a fascinating field, full of potential and mystery. As we stand on the brink of this new era, one thing is certain: the quantum revolution is just getting started.